welcome you all. In this particular lecture, we are going to start the Fourier series. If you see earlier, we have done the Laplace transform, inverse Laplace transform, convolution theorem and the solution of ordinary differential equation using Laplace transform. These things we have covered in the earlier lectures. Now, we are going to start the other one, that is Fourier series. What is a Fourier series? In many engineering problems, it is necessary to express a function as a series of sine and cosine functions. Please note this one, that if a function is given to us f x, we can express it in terms of sine series and cosine series. That series we call it as the Fourier series. If you see this type of series, we call it as Fourier series, which was first developed by French mathematician cum physicist Joseph Fourier in 1822. So, Fourier series was developed by the French mathematician Joseph Fourier in the year 1822. Now, for the Fourier series, we take a formula which we call as the Euler's formula. The Fourier series of a function f x in the interval alpha to alpha plus 2 pi is given by f x equals a 0 by 2 plus summation n equals 1 to infinity a n cos n x plus summation n equals 1 to infinity b n into sin n x. So, a Fourier series we are defining in the form of f x equals a 0 by 2 plus summation n equals 1 to infinity a n cos n x plus summation n equals 1 to infinity b n sin n x, where the coefficients a naught, b n, a n and b n are defined as a naught equals 1 by pi alpha to alpha plus 2 pi f x dx, a n equals 1 by pi alpha to alpha plus 2 pi f x into cos n x dx, and similarly your b n is 1 by pi alpha to alpha plus 2 pi f x into sin n x f x sin n x dx. So, please note that a series f x is given, a function f x can be represented in terms of sine and cosine series in the form of f x equals a naught by 2 plus summation n equals 1 to infinity a n cos n x plus summation n equals 1 to infinity b n sin n x, where a naught is 1 by pi alpha to alpha plus 2 pi f x dx, a n equals 1 by pi alpha to alpha plus 2 pi f x cos n x dx, and your b n equals 1 by pi alpha to alpha plus 2 pi f x sin n x dx. This we call as the Fourier series of the function f x. So, just if you see your f x is this and f x equals a naught by 2 this thing plus n equals 1 to infinity a n cos n x plus summation n equals 1 to infinity b n sin n x, where a naught is this, a n is this and b n is this one. Now, to establish this formula, that f x equals a naught plus summation n equals 1 to infinity cos n x plus summation n equals 1 to infinity b n sin n x, where a naught, a n and b n are these. To prove this one, we need to know certain standard values of some definite and integrals. So, let us see the values of those integral first. Number 1, alpha to alpha plus 2 pi cos nx. What is the value of this? Alpha to alpha plus 2 pi cos nx dx. This is nothing but the sin nx by n, sin nx by n alpha to alpha plus 2 pi. And if you put the limits, the value will be 0. So, please note that alpha to alpha plus 2 pi cos nx dx, this is equals 0. Similarly, alpha to alpha plus 2 pi sin nx dx, this is equals, again just I am brushing up these things, I am not giving the proof, cos nx by n alpha to alpha plus 2 pi, and this value is again equals to 0. So, alpha to alpha plus 2 pi cos nx dx is 0, alpha to alpha plus 2 pi sin nx dx, this is equals to also 0. The next one is alpha to alpha plus 2 pi cos mx into cos nx dx. Obviously, we will assume that m is not equals to n here, and if you do this thing, this will be alpha to alpha plus 2 pi cos of m plus n into x my plus cos of m minus 1 m minus n into x dx. If you integrate this you will get half into sin m plus n into x by m plus n plus sin, this will be sin m minus n into x by m minus n, where limit will be alpha to alpha plus 2 pi, and this value is equals to 0 for m not equals n. So, please note that alpha to alpha plus 2 pi cos mx cos nx dx, this is equals 0 for m not equals n. The next one is number 4 is alpha to alpha plus 2 pi cos square nx dx. This equals, if we integrate, this will be x by 2 plus sin of 2 nx by 4n. This is 4n alpha to alpha plus 2 pi. And if you put the limits over here, you will get the result as pi. Therefore, alpha to alpha plus 2 pi cos square nx dx, this is equals to pi. Number 5 is alpha to alpha plus 2 pi sin mx into cos nx dx. This, if you integrate, you will get cos of m minus n into x by m minus n plus cos of m plus n into x by m plus n and alpha to alpha plus 2 pi. And if you evaluate the limit over here, you will get the value as 0. Therefore, alpha to alpha plus 2 pi sin mx cos nx dx, this is equals to 0. The next one is number 6 is alpha to alpha plus 2 pi sin nx cos nx dx. So, if you evaluate the limit over here, this is sin square nx by 2n alpha to alpha plus 2 pi, and this value again will be equals to 0. So, alpha to alpha plus 2 pi sin nx cos nx dx, if I evaluate the integral, this value is equals to 0. Number 7, alpha to alpha plus 2 pi sin mx into sin nx dx, sin mx into sin nx dx. Of course, we are assuming here that m is not equals to n. So, if I evaluate the integral in this case, sin of m minus n into x by m minus n minus sin of m plus n by sin of m plus n into x by m plus n alpha to alpha plus 2 pi. And if I evaluate the limit, this is equals to 0 when your m is not equals to n. Therefore, alpha to alpha plus 2 pi sin mx sin nx dx, this is equals to 0 whenever m is not equals to n. The next one is alpha to alpha plus 2 pi sin square nx dx. The value will be again similar type, x minus 2 by sin twice nx by 4n alpha to alpha plus 2 pi, and the value is equals to pi when n not equals 0. So, please note this useful value of these definite integrals, which we will use frequently afterwards. For that reason, we just told this thing. So, you just brush up. To establish the formula, we are just as we have told, alpha to alpha plus 2 pi cos nx dx equals 0, alpha to alpha plus 2 pi sin nx dx, this is equals 0. Number 3, alpha to alpha plus 2 pi cos mx cos nx dx, this is equals 0 when m is not equals to n. Alpha to alpha plus 2 pi cos square nx dx, this equals pi. Alpha to alpha plus 2 pi sin mx cos nx dx, this value is equals to 0 whenever m is not equals n. Alpha to alpha plus 2 pi sin nx cos nx dx, this is equals 0. Number 7, alpha to alpha plus 2 pi sin mx sin nx dx equals 0 when m is not equals to n. And number 8, alpha to alpha plus 2 pi sin square nx dx equals pi when n is not equals to 0. Now, using these integral values, now let us establish the formula f x equals a 0 by 2 plus summation n equals 1 to infinity a n cos n x plus summation n equals 1 to infinity b n sin n x. So, f x we are representing in the interval alpha to alpha plus 2 pi as a Fourier series in the form f x equals, we are writing a 0 by 2 plus summation n equals 1 to infinity a n cos n x plus summation n equals 1 to infinity b n into sin n x. So, we have to find out the values of the coefficients a naught, a n and b n. This is our job. To find the value of a naught, a n, b n from this given series, first we want to find out the value of a naught. So, we will integrate the both side of this equation, say this is 1, both side of the equation from alpha to alpha plus 2 pi. So, that you can write down alpha to alpha plus 2 pi f x dx. This is equals 1 by 2 a naught will come here, alpha to alpha plus 2 pi into dx plus summation alpha to alpha plus 2 pi summation n equals 1 to infinity a n cos n x into dx. This I can put it inside this bracket plus alpha to alpha plus 2 pi summation n equals 1 to infinity summation n equals 1 to infinity b n into sin n x into dx. Now, this value is equals to half a naught into this will be x, so alpha plus 2 pi minus alpha. So, that this value will become 2 pi, value of this first integral. Value of the second integral is 0, this is equals to 0, this value is also 0. That is, you will directly get it from our formula whatever we told, definite integrals 1 and 2. So, that you are obtaining the value as 2 will be cancelled, a naught into pi. So, from here I can tell that my a naught equals 1 by pi alpha to alpha plus 2 pi f x dx. So, you got the first formula, that is a naught equals 1 by pi alpha to alpha plus 2 pi f x dx. Now, to obtain, I have to find out the value of a n. To find the value of a n, what I will do, on the equation 1, I will multiply both sides by cos n x and integrate from alpha to alpha plus 2 pi. So, therefore, to find out the value of the coefficient a n, we will first multiply the equation 1 by cos n x on the both side and then integrate from alpha to alpha plus 2 pi. So, once we are doing it, on the left hand side you will get alpha to alpha plus 2 pi f x into cos n x dx. On the right hand side you will get half a naught into alpha to alpha plus 2 pi cos n x dx plus alpha to alpha plus 2 pi summation n equals 1 to infinity a n cos n x into cos n x dx. Cos n x dx plus alpha to alpha plus 2 pi summation n equals 1 to infinity b n sin n x into cos n x dx. Using the definite integrals over here, what you will get, value of this integral will be 0, the first value will be 0 if you see the values of the integrals from there. Here it is cos n x into cos n x dx is there. Whenever m not equals n, then this value will be 0. So, that only one term you will get, that is a n into pi you will get, and the value of this integral again, this is also 0. So, that ultimately you are getting the value as a n into pi. So, using your 1, 2, 3, 4, 5, 6, all these definite integrals whatever I told just now, using those you will obtain a n equals pi. So, that you can write down a n equals 1 by pi alpha to alpha plus 2 pi f x into cos n x dx. So, we got the value of a n as 1 by pi alpha to alpha plus 2 pi f x cos n x dx. In the same way, whenever I want to find out the value of the coefficient b n, I will multiply the equation 1, that is f x equals a naught by 2 plus summation a n cos n x plus summation b n sin n x by sin n x on both sides of the given equation and integrate from alpha to alpha plus 2 pi on the both side. So, by multiplying by sin n x on the both side and integrating, you will obtain alpha to alpha plus 2 pi f x into sin n x dx. This is equals half into a naught into alpha to alpha plus 2 pi sin n x dx plus alpha to alpha plus 2 pi summation n equals 1 to infinity a n cos n x 1 to infinity a n cos n x into sin n x dx. sin nx dx plus alpha to alpha plus 2 pi summation n equals 1 to infinity bn sin nx into sin nx dx. If you evaluate the integral, again you will see that this term vanishes, this will vanish, here also except for n equals n, all other terms will vanish. So that you will get 0 plus bn into pi. So that you are ultimately obtaining bn into pi, and from here you can write down bn equals 1 by pi alpha to alpha plus 2 pi fx into sin nx dx. So, by this way we establish the formula for the Fourier series, that alpha to alpha plus 2 pi if fx equals a 0 by 2 plus summation n equals 1 to infinity a n cos nx plus summation n equals 1 to infinity b n sin nx, then a naught a n and b n can be these coefficients can be evaluated by this integral. The next one you see some special cases of this. If we take alpha equals 0, say, initially whatever we assume, that is alpha to alpha plus 2 pi. So that whenever alpha is equals to 0, so your x varies from 0 to 2 pi. Since alpha is equals to 0, your original was alpha to alpha plus 2 pi. So, now x varies from 0 to pi. So, you can write down in this case your a naught will be 1 by pi, this is will be 0 to 2 pi. Please note this one, earlier it was alpha to alpha plus 2 pi. Now, it will be from 0 to 2 pi fx dx, a n will be equals to 1 by pi 0 to 2 pi fx into cos nx dx, and your bn will be equals to 1 by pi 0 to 2 pi fx into sin nx dx. So that whenever I am getting a special case alpha equals 0, then the x varies in the range from 0 to 2 pi and a naught, a n and b n, the integrand will remain same, but the limit will be from 0 to 2 pi. Case 2, if you take your second case, case 2, if alpha equals, we consider minus pi. In that case, your x will vary from minus pi to pi, because originally we have made it alpha to alpha plus 2 pi. So, in this case, your a naught you can write down 1 by pi minus pi to pi fx dx, a n equals 1 by pi minus pi to pi fx cos nx dx, and your b n will become 1 by pi minus pi to pi fx into sin nx dx. So, effectively we have done the generalized case, and in the generalized case we are using this thing, that in one case we have done in the alpha to alpha plus 2 pi, then I can assume that alpha equals 0, then the range of x will be from 0 to 2 pi. I can assume alpha equals minus pi, in that case my range will be minus pi to pi. In these all cases, only change will be the limit of the integration changes. In one case it is alpha to alpha plus 2 pi, in the second case it is from 0 to 2 pi, and in the third case it is minus pi to pi. So, let us see this thing. So, this was the, so for the proof, as I was telling you, fx is represented in the interval alpha to alpha plus 2 pi by the Fourier series as fx equals a naught by 2 plus summation n equals 1 to infinity a n cos nx plus summation n equals 1 to infinity b n sin nx. To find the coefficients a naught, a n and b n, we assume that the series 1 can be integrated, this I forgot to tell, can be integrated term by term from x equals alpha to alpha plus 2 pi. This assumption we have to make that the term by term integration is possible. Just after this proof, maybe in the next lecture we will see that what is the proof of the condition for which Fourier series exist. Next, to find a naught, we have to integrate both side of 1 from x equals alpha to alpha plus 2 pi. So that you will obtain alpha to alpha plus 2 pi f x dx equals half a naught into alpha to alpha plus 2 pi dx plus next integral where summation is on a n cos n x dx plus summation of b n sin n x. If you see, the value of the first term is only alpha. If I put the limit alpha plus 2 pi minus alpha, and from the definite integral values which we did just now, the first value will be 0, the value of the second integral will be 0, value of the third integral will be 0. So that you will obtain the value as a naught into pi. So, I can write down a naught equals 1 by pi alpha to alpha plus 2 pi f x dx. Similarly, to obtain the value of a n, I will multiply both sides of equation 1 by cos n x and integrate from alpha to alpha plus 2 pi. Then you will obtain this integral. Here again, if you see, the first integral and the third integral both will be 0. Only for the second integral we will get a term for a n, that is a n into pi, and the first integral and the third integral will be 0. For all other terms of a n also will be 0. So, once I am getting a n into pi, I will obtain this value a n equals 1 by pi alpha to alpha plus 2 pi f x cos n x dx. For the third case, to find the b n, we will multiply both sides of the given equation 1 by sin n x and then integrate from alpha to alpha plus 2 pi. On the same fashion, here the first integral and second integral of the right hand side will be 0, and for the third integral only we will get one term, other terms will vanish. So, I will obtain b n into pi. So, that I can tell b n equals 1 by pi alpha to alpha plus 2 pi f x sin n x dx. So, this establishes the formula f x equals a naught by 2 plus summation n equals 1 to infinity a n cos n x plus summation n equals 1 to infinity b n sin n x, where a naught, a n and b n are being given. As a special case, if I make alpha equals 0, then the range will be of x will be from 0 to 2 pi, a naught, a n and b n, the integrands inside the integral will remain same, only the limit will change to 0 to 2 pi. Similarly, if I make alpha equals minus pi, then a naught, a n and b n will be this thing, only thing the limit of the integral will be from minus pi to pi. In the next lecture, we will see how for which condition the Fourier series of a function exists, whether Fourier series of a function exists for all functions or there are certain criteria are there or not, that we will see in the next lecture.